Hi, good morning, students. So, in the last class, we discussed about electrical instruments like measuring instruments. We solved some problems in the last class. We solved some problems based on the potentiometer concepts. So now let us go to the next topic here in the current electricity. It is a heating effects of current. So generally, we know when current is passing through some resistor or any wire, some heat energy will be produced in this. So the temperature of the wire will rise there by absorbing that heat energy, and so that is nothing but we call the heating effects of this current here. So the heating effects of current is nothing but when current is passing through these conductors or any resistors, then heat energy will be produced in this, and so then that is nothing but we call the heating effects of this current, right? And so that heating that is also called Joule heating. The heat produced here is nothing but actually we call that as Joule heating. And here we know in our daily life there are many devices which works on the principle of heating effects of this current. So such as nothing but geyser or iron box, heater, or some devices like which are works on this which are works on this examples for this devices which are works on this heating effects. And now there is some advantage of heat energy. At the same time, there is some disadvantage of heat energy. When you are transferring power from one place to another place, some loss of energy will take place there, which we can't use. So, right. And so now, if you want to go to the reason or cause why this heat energy is produced in that resistor, means we need to go back to our introduction to this topic here, or introduction to this resistor here. So let us discuss about the cause of this heat energy. So now up to here what we are concluding is whenever heat is flowing through a wire, some definitely some current is flowing through a wire, heat energy will be produced in that. And such a heat is nothing but we call Joule's heat energy, Joule's heat. And so now it is nothing but we can let us see the reason for this. Why this heat energy is produced in this. So you know when like this, when current is flowing through this conducting wire, some heat energy will be produced here is. So here this heat energy, like in the during this transmission of this power, this amount of heat energy will goes as wastage. You can't use this amount of heat energy here. So that means it's a loss of heat energy here, right? So that means there are certain losses of heat energy will take place there. At the same time, there is some advantage of this heat energy also. Like here, if we know this iron box, so iron box works on the principle of this heating effects of the current. And next this toaster also works on the principle of heating effect, and this filament bulb. And so then this filament bulb also works on the principle of this heating effects. When current is passing through this filament, heat energy will be produced here. And so that heat energy, because of that amount of heat energy, it will causes some light produced there. And so then another example is this lighting here during this thunderstorm. If thunderbolt appears here, then because of this some heat energy will be produced here. That means because of this sometimes you can observe that this trees also catches some fire here because of this heating effects, right? So those are the examples of this heating effects of this current here. Basing on this heating effects of the current, then there are some advantages or there. At the same time, there are certain disadvantages or there. Loss of power will take place there in this. And so now, if you are coming back to this cause of this heating energy, that actually this heat energy produced here is, as I said, this is nothing but we call this Joule's heating here, or Joule's heat. The amount of heat energy produced is nothing but we call Joule's heat here. So this Joule's heat is nothing but because they actually this regarding this certain amount of heat energy is produced in a conducting wire. When a current is passing through that is discovered by this Joule here, and he did a lot of work based on this. And so then we call that as Joule's here and Joule's heat. And the cause for the basic cause, he identified it as a collisions there. So the basic cause for this heat energy is nothing but collisions. We know when current is passing through that material, then there are a lot of lattice atoms will be there. Lattice atoms or ions will be there. When electron is moving through this material, then it undergoes a lot of collisions, which we discussed in the beginning of this topic here. And so now this because of these collisions, it will follow this zigzag path there. And at the 12 last year also we discussed about that. So it follows some zigzag path like that. So the electron will make one collision and then it changes its direction and it loses a parts of energy to that lattice atom there. That means the each collision it loses energy, and then it changes its direction, and that atom, that energy is gained by this lattice ion there. And so by absorbing that lattice ions, and again the electron will accelerate here because of this electric field, again electron will gains the energy, and again it loses energy because of this next collision. So by absorbing this energy, this lattice atoms or ions will exhibit this the amplitude of vibration of this ions will increase there. And so when ions amplitude is increasing, but increasing means that is nothing but the temperature of the material increase. When the temperature of material increase, then only this vibration of these atoms, amplitude of vibration of the atoms will increase there. So that is nothing but basic reason for this Joule's heat here, because of this atomic, because of the collisions of these electrons, because of the collisions of these electrons, then it will be produced there. So that electronic collisions is the basic cause for this Joule's heat here. So because of the collisions, when electron is moving through the material, the electron will undergo a lot of collisions, and because of that collision, it loses a parts of energy to these atoms or ions, and so that energy is transferred to the material. So bulk material, that means to the wire, and so because of that, the temperature of the wire will increase there. And so now let us see how to derive an expression for heat or heat energy or electrical energy produced in a resistor. So now suppose we are considering that current I is flowing through a resistor and dq is a current flowing, dq is the charge flowing between them, points which are differing by a potential of V in the time dt. Then we know work done formula we already derived in electrostatics. So work done we can express it as V is equal to dq formula we can write here. Work done is equal to, so dW is equal to, for small amount of charge or small amount of work done we are writing here. So therefore this dW is equal to V into dQ we can write, and we know this dQ we can write it as I into dt, because I is equal to dQ by dt we can write here. So to get this total energy, total amount of work done, we can integrate this here. By integrating this, we can write this as V into I into dt we can write. If suppose this V and I are constants, then we can write them outside here. So V into I into integral of dt, and so that this value we can write this as W is equal to VIT we can write here. So this is the amount of work done, and this amount of work done is nothing but we can take it as heat produced in this. So heat produced in this resistor, we can write this as, in the given time interval we can write it as VIT, or this is nothing but we can express this as I square RT, right? And so now this is nothing but our Joule's heat expression here. So this is nothing but we call this as Joule's heat expression. So V is equal to, or you can also write here, you can also write this as so you can also express this equation as V square by R into T. That means you can express it in different ways like this. So then this is nothing but we called expression for this heat energy here. All these three are same only. You can use it as either VIT, or you can use it as I square RT or V square by RT. When you are comparing heat energy produced in the different elements, then which formula you need to take means that depends on that. Suppose if you are taking the two resistors, so two resistors if you are taking in series, if they are connected, then we can say this heat produced in them we can compare by using this equation, because when they are connected in series, then I will be same amount of current will flow through them, then this H is directly proportional to R into T we can write. And or if in the same time if you are comparing, then H is directly proportional to R you can write there. But whereas if the same two resistors are connected in parallel, so then you know in parallel means then the potential difference will be constant, then you can consider this expression here. Then V is constant, so H is inversely proportional to R there. So that depends on the given situation, whether we need to take either V square by R into T or VIT or I square RT. But basically this I square RT is nothing but we call the Joule's heat expression, or this is nothing but we call the Joule's law here. That means here this H is directly proportional to square of the current, and H is directly proportional to the resistance, and H is directly proportional to the time here. For a given resistor, this is the generally the Joule actually derived this expression, and he concluded this point here. For a given resistor, if I is a current flowing through this, he is not comparing with any other resistor. For a given resistor, he is concluding here. Then amount of heat energy produced in this resistor will depend on the current flowing through this, and it also depends on the how much time this current is flowing through this. So then he concluded this expression here. H is directly proportional to I square, and H is directly proportional to R, and H is directly proportional to this T time. So then this is nothing but our Joule's heat expression here, right? And similarly, we can discuss about power expression here, power produced in this. And you know the definition of this power, that power is nothing but rate of heat produced or rate at which energy enters in this circuit, or rate at which that heat is produced in that. So that power we can write it as dq by dt, or which we can write it as vi by using our dw expression. So dw expression we are writing like this, vi into dt, and dw by dt means we can write this as vi. And so now here, therefore, this by using Ohm's law, V is equal to IR, we can write here. So say again, this power expression we can write this as in three different forms here. Either you can write this as VI, or I square, or V square by R we can write here. So that is a power expression. Just we need to divide this expression, this heat expression, with the time. And so generally when the current is constant and all are constant, when current is constant and time is, that means resistance is also constant, then we can use generally this heat energy means I square RT formula we can use. But whereas when current is variable, that means anything such a variable quantities are there, then in general we need to write this expression as that heat produced, we need to write it as for the small time interval we write here the heat produced expression, integral of like I square into R into dt, and then this total heat energy means we need to write this as integral of I square R into dt we need to write. That means we use this integration here. If any variables are there, that sometimes like current may be variable in some problems. So then if it is variable, then we need to calculate this amount of heat energy by using this expression here, right? So that is about this electrical energy and power here. So this is nothing but again the reason I am giving here, the reason which we discussed now, and this is nothing but Joule's heating effect here. And so now let us see this units of this electrical energy and electrical power here. And you know the energy, the unit of this electrical energy may be different units we can use here, joule, calorie, and kilowatt hour, etc. That means different forms of, that means it is also a form of energy, so we can use the different units of this energy. And you know already this relation, 1 calorie is equal to 4.18 joules, or generally for solving the numericals we consider that as 4.2 joules. Now let us see the relation between kilowatt hour and a joule. So then 1 kilowatt hour means, you know, the 1 kilo means 1000 watts, and this watt is and this hour, and hour value we can write like this, 60 into 60, so it is 3600 seconds. And so now this can be expressed as 3.6 into 10 power 6 watt second. That you know watt second is nothing but you can write it as joule here. And so then 1 joule, 1 kilowatt hour is equal to 3.6 into 10 power 6 joules we can write here. So that is a relation between 1 kilowatt and the joule here. So finally what we are concluding is 1 kilowatt is equal to 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. So it is a relation between kilowatt hour and the time. And so important thing here you need to remember is kilowatt hour is a unit of energy, not the unit of this it is not the unit of power here. Watt kilowatt is a unit of the power, but watt hour is a unit of energy, because we are multiplying this power with the time here. We are multiplying with this time, this hour. So that is nothing but it becomes that energy there. And actually this for this our household consumptions, generally for the commercial unit of this electrical energy is nothing but we use this kilowatt hour here. So this 1 kilowatt hour is nothing but for our households. You know, when you are seeing the monthly bill, you will get like how many units of this electrical energy is consumed, like 200 units or 250 units or 500 units or 1000 units. So they will mention in terms of that units there. So that means that one unit of this commercial unit is nothing but 1 unit is equal to, you can say, 1 kilowatt hour here. So that means this 1 kilowatt hour only is taken as a unit, 1 unit. So that is nothing but we know we mention it as a commercial unit. So this 1 kilowatt hour is taken as a commercial unit here. So the number of units you can write like this, watt hour by 1000. That means we are giving this, we are converting this into like just by using this conversion you can convert this into kilowatt hour. That means sometimes if they may ask that how many units of electrical energy is consumed. So then by using, first we convert this, how much amount of energy is consumed, you may convert this into generally you will get such a problems you will get in watt hours you will get here. That is why I am giving this conversion here. Like suppose a tube light of 40 watts is there and it is used for a 8 hours a day, right? And so now here suppose then for day how much energy is consumed means this is 8 hours. How much energy is consumed means then directly you can write this as 40 into 8. So this is the energy consumed per day, right? If suppose for 10 days if I am asking here, then you need to multiply with this 10. And so now this how many watt hours will be there? Then 3200 watt hours will be there. Then to convert this into kilowatt hour, then what we need to do is we need to divide with the 1000 here. Therefore, you will get this value as 3.2 now kilowatt hour. That means if you are taking a tube light, for example, tube light of 40 watts and it is used 8 hours a day, and then number of units consumed in one day will be 40 into 8. That means 40 into 8 watt hours. That is the amount of energy consumed. If suppose if they are asking for 10 days, then into 10. So that you will get this unit as watt hour here. Then to convert this into kilowatt hour, then we are dividing with this 1000, so that you will get this value as kilowatt hours you will get here. So sometimes there may be some problems based on this. They will give the device and like a refrigerator or geyser or AC, they will give the devices and they will ask like how much electrical bill will be there per month. So then per month means we calculate like this. If suppose this a refrigerator is 2000 watts is given here, the rating of this refrigerator, then 2000 into then how many hours it is consumed per day, that also they will mention that. So then suppose it is used for a 20 hours a day, or if suppose if it is running continuously, then 24 hours you can consider there. So then they may give the time here, then according to the time, and keep that what here the simple process, you may keep this time in hours only, so that first if you are multiplying these two, then you will get in watt hour, right? You will get in terms of this watt hour, then you can convert this value as in terms of this kilowatt here by dividing with this 1000, so that you can convert this number of units consumed, you can write there in such a case. So then that is about this conversion of this or finding this number of units there. And so then here next the unit of this electrical power, you know the electrical power unit, watt, kilowatt or megawatt. And so then such a different units we use here, or sometimes we use the horsepower generally to express the power of these pumps, motors. We use this horsepower unit. And so then kilowatt means all these are just multiples only. 10 cube watts you will get, mega means 10 power 6, and 1 horsepower means 746 watts you will get. That's already, right? So it is a conversion of these units there. And here next mention a note here, like suppose here I am giving this first note, suppose I am taking this H is the amount of heat energy produced in a resistor R, right, in a given time interval. So mention that let H be the amount of heat energy produced. Let H be the amount of heat energy produced in a given resistor. So in the resistance R, here amount of heat energy produced in the resistance R in the given time interval T. In the given time interval T. Then the total amount of heat energy produced when such n identical resistors, when n such identical resistors are connected in series with the same source is given by. When n identical resistors are connected in series with the same source, is given by. That means here for one resistor the amount of heat produced is given here. So for one resistor we can write this amount of heat produced as I am taking this V square by R into T here. V square by R into T, because the given condition is for the same source. Now we are connecting this n resistors here. Suppose initially this one resistor is connected like this. Now across the same source we are connecting like n number of resistors here. So here n number of resistors or identical resistors are connected across the same source. So then if you are taking I square RT, then I in the first circuit and I in the second circuit will be different there. So first you need to calculate the I value if you are using this I square RT there, right? So then instead of this what I am taking is H is equal to I square RT I am taking here. And so then next we can write this as, suppose this value I am taking it as H dash. So V square by R effective into T we can write. In the second case, when n identical resistors are connected here. So V square by this R effective, NR it is. So therefore this H dash is equal to, you can write this expression as H by N we can write here. Got it? V square by R into T is nothing but this H. So then number of, that means total amount of heat energy, this is the total amount of heat energy produced in all resistors. The total amount of heat energy produced in all resistors will be equal to H by N when N resistors are connected in series here. So this is the point you need to remember here. So that is the right, note down this calculation. And next I am taking in the same case, for example, if all such N resistors are connected in parallel. So let us see this amount of heat energy. So next mention that in the above case, if all the resistors are connected in parallel across the same source, in the above case, if all the resistors are connected in parallel across the same source, then total amount of heat produced is given by. Then total amount of heat produced is given by. So then again I am taking this as some H double dash here in parallel. So again I am taking the same formula here, V square by this R effective into T we can write. And so now V square by R effective is when such a N resistors are connected in parallel, then R effective value we can write this as R by N, right? In resistors we know already this. So therefore this amount of heat produced we can write this as N into V square by R into T. So which you can express this as amount of heat produced is equal to N times the H here. Say N times that initial, that means N times the heat energy produced in a single resistor. So in single resistor, H is the amount of heat energy produced. But when you are connecting such N resistors in parallel, then amount of heat energy will increase by N times here. Whereas when they are connected in series, it decreases by N times here. Now sometimes they may ask the same questions in a different way here. So write that as the next point in that. Again same, first initial conclusion will be same. Let H be the amount of heat energy produced in a resistor or in the given time t. Let H be the amount of heat energy produced in a resistor or in the given time t. Now this resistor is divided into n equal parts or n identical pieces. This resistor is divided into n identical pieces. If one of the pieces is connected across the same source, if one of the pieces is connected across the same source, then find heat produced in it. Then find heat produced in it. Right? So then now see this. Then H is the amount of heat energy produced in a single resistor when it is connected across the source. So we can write V square by R into T. Now here this H dash is equal to, again what we can write is V square by R effective into T. Now can you say when you are dividing this resistor into n times here, when you are dividing this resistor into n times, the effective resistance, that means resistance of this each part will be equal to R by N. We know this resistance is directly proportional to length, so that this resistance is also reduced to this N times here. Therefore, this amount of heat produced we can write this as V square by, this is R by N into T. And so this is again N into V square by R into T you can write here. Therefore, this amount of heat produced we can write this as N times that of heat produced in a single resistor. In a total original resistor here, in original resistance if it is N, if you are taking this one piece of that resistor after dividing that into N parts, then you will get that heat energy as N times that of the original resistor. Now here again another condition is there, right? In the same, after dividing that into N equal parts, so next note that if all such a pieces are connected in parallel across the same source, if all such a pieces are connected in parallel across the same source, then amount of heat energy produced is given by. Then amount of heat energy produced is given by. So then here what you can write here is, see this again H dash is equal to V square by R effective into T. So now each resistance is R by N. Such n resistors are connected in parallel here. That means R by N, R by N, R by N. Such n resistors are connected in parallel. Therefore, then in that case, this effective resistance we can write this as R by N square here. So that is the effective resistance when such R by N are connected in parallel. So that we can write this as V square by R by N square into T. And therefore, this value we can write this as H double dash is equal to N square into H value we can write here. So this amount of heat energy produced, total amount of heat energy produced when all such N pieces are connected in parallel, right? So the same question they ask in terms of the power. The power also, then just you will get the same H value you need to replace with the H term you need to replace with the P here. That is only the difference there. There is no any the calculation, everything will be same. Just instead of T, that means we need to eliminate the T value here. Then you will get this term as power. H by T is nothing but our power here, right? So then remember this. So next, let us see here if you are taking some source, then power output of a source here. Just we are taking just a battery here. So then in this, let us see how much of amount of heat energy output, amount of power output will be there here. Just we are taking some, this is the battery here, and this battery and internal resistance we are representing here. This is a positive terminal of battery of EMF here, and this is a negative terminal. Now it is connected to some external source. That means like some resistor. And so now here it is, now the discharging of the cell is taking place here. When the discharging of the cell is taking place, then power output we are writing here. The power output of the cell is nothing but P is equal to V into I we can write. And V is nothing but terminal voltage here. The terminal voltage we need to write here. So that it is nothing but E minus IR you can write. So E minus IR is the terminal voltage when the cell is discharging. We know already. Therefore you can substitute here. Therefore this is the power output here. The power output of this cell is nothing but you can write E minus IR into I. So which is nothing but given by this expression here. Therefore this power output is nothing but, so output power is so power output is E into I minus I square R. Whereas if suppose if I ask that what is the rate at which chemical energy is converting into electrical energy, or I can mention here as first let us write this as power loss here. How much loss is taking place here? Power loss. So that power loss we can write as power is taking place loss at this internal resistor. So you can write this as I square into R, because this IR is a loss of volts. We discussed already in the discharging of the cells when you are discussing about the cells. So then IR is a loss of volts. So that because of that, or because of this heat produced at the internal resistor, that will goes as a wastage for us. And so then power loss we can write it as I square R here. So the total power delivered by the cell, or this is total power. So total power is nothing but output power plus this loss. And so which you can write this as EI. This I square R term will be cancelled here. Sorry, this is smaller. In output term you need to write this as smaller. I square into smaller. And so now here this is nothing but now VI is the power delivered by the cell here. That means that means total it can produce the VI, but out of that the useful power is only this value here. This is the loss of energy and this is the useful power. That is nothing but we are giving as output. Output is nothing but the useful. So that means useful power is EI minus I square R, whereas the loss is nothing but I square R here. So then sometimes they may ask that rate at which chemical energy is converting into electrical energy. So this is nothing but the rate at which chemical energy is converting into electrical energy there, right? So whatever the power, the total power it is delivering, so that chemical energy is converting in that rate here. So EI we need to write. And next, suppose when the cell is in discharging and the charging state. The previous discussion is when the cell is in charging state, right? So now when the cell is in discharging, when this case is now when the cell is in charging state. Charging state, you means this power should enter, the current should enter into the positive terminal of the battery here. Then the circuit is said to be in, that means battery is said to be in charging state. In case of the charging case, again we can write it as power input. Now we are writing here. We are supplying some power to the battery from external source. So power input to the battery is nothing but, again our formula is nothing but Vi, where V is a potential difference across these two terminals of the battery. And when the cell is in charging state, the potential difference we can write it as E plus IR. We already discussed about this terminal voltage, how to write terminal voltage when cell is in charging state or discharging state or in short circuit or in open circuit. So in charging state we need to write it as E plus IR. Therefore power input is equal to, we can write this as E plus IR into I. So then EI plus I square R. So whatever the loss is there, so that loss is also we are supplying from the external source only. Like suppose, let us say you are supplying some 100 watts of power here. Out of this 10 watts is lost at the 10 watts of power is lost at the internal resistor. Then only 90 watts of power will be stored in that cell. But totally, that means total power supplied means, or total input means, we need to write these two values here. The total energy stored in the battery or cell, or the total power produced at the internal resistor. Both we should write, because these both are supplied by this external source only here. External source only supplying this these two values there, and so that we need to add those two values here. What we are getting here, EI, this is the power, actual power to the source, and then this is a loss of energy here, loss of energy at this cell, right? So this is the power input. So in case of input, you will get the plus sign here, and when you are writing this output, you will get this negative sign here. Remember these cases carefully there. And next here, let us see this maximum power transfer theorem. And we discussed already in case of the cells. In case of cells, we discussed already about this maximum power transfer theorem. And let us see in case of a simple circuit now again here. Because now instead of group of cells, there may be group of resistors connected in that combination there in that given circuit. And so now let us see this. Suppose here we are taking a simple circuit here. A cell of EMF and resistance R is connected to external resistance R, capital R. And then we can write the current produced in this, current passing through this circuit is nothing but, we can write this as E by R plus R, we can write. Therefore power produced or power consumed by this resistance here, the power produced at the resistance, or we can say that power consumed at that resistor. So then that we can write it as I square R. Then I value you can substitute here, E square R by R plus R you will get. And general processor, when this power is maximum, then its differentiation with respect to R is 0. So here R is variable here. We need to take a suitable resistance so that the power is maximum here. And so that we are taking this, that means these two are fixed here, then this small r, capital R is variable here. So we are finding the differentiation of P with respect to this capital R. And the differentiation, so once if you differentiate, then you will get this small r is equal to capital R there. So that condition actually we know already in case of cells. So here also once again we are getting such a condition here. The total external resistance should be equal to internal resistance in that circuit. So that you will get this power in that circuit will be maximum, and which we call that as maximum power transfer theorem. That means that is our conclusion here. When total internal resistance in the circuit, effective internal resistance in the circuit is equal to external resistance, then power in that circuit will be maximum. The power consumed in that circuit will be maximum here, right? And so then the maximum power you can calculate it by substituting this R value here. So then by substituting this capital R is equal to small r here, you can calculate the maximum power consumed there. So you can write this as V square by R into R plus R. So this is small r plus small r you can write. Or if you want to express in terms of this capital R, you can express in terms of the capital R, because small r and capital R equal only. And if you draw the actually graph between this power consumed and this resistance, then you will get this case like this here. You will get this parabolic, that means this is the curve here. This is actually this relation here. So you will get a curve like this. When small r is equal to capital R, then you will get this maximum power here. So that is our conclusion here. That means small r is equal to capital R means when effective internal resistance in the circuit is equal to external resistance, then power consumed in the circuit will be maximum. So you may mention that statement again here. We mentioned already at the mixed grouping of the cells. So again write that. After here you may mention that statement there. Therefore, when effective internal resistance in the circuit is equal to external resistance, effective internal resistance in the circuit is equal to external resistance, then power consumed in the, then power delivered to the external resistance is maximum. Then power delivered to the external resistance is maximum. This is called maximum power transfer theorem. Maximum power transfer theorem, right? And at the cells, actually we discussed the different cases there, when the current becomes maximum, when small r is variable, and when capital R is variable. So we discussed those cases already, right? So like suppose I am taking the case, this capital R is variable here. So this capital R is variable. This is nothing but what we discussed in the previous case here. This is EMF here and resistance R. So therefore this I maximum will be equal to this E by R. Sorry, small r, right? When small r is variable, you will get the maximum current when small r is equal to, when this capital R is equal to 0 here. This is the maximum current, right? And whereas this maximum power is nothing but when maximum power is nothing but you will get like maximum power you will get when small r is equal to capital R here. When small r is equal to capital R, then you will get the maximum power delivered to this external resistor. Here current will be maximum only, but here there is no external resistance to deliver the power here. That means no power will be delivered to this external resistance. The external resistance itself is not there. The cell is short circuited in this case when small r is equal to 0, right? And so that if they ask about the maximum current when this small capital R is variable, this is a condition when you will get the maximum current, and maximum power you will get when small r is equal to capital R. And whereas suppose I am taking the case like this small r is variable here. So this capital R is fixed here. This is a fixed value. It is having some fixed value. Now this small r is variable here. We can vary this small r here. Then automatically we can say that current in the circuit will be maximum for this case here. Current will be maximum, which is equal to E by R when capital small r is equal to 0. Whenever that simply in the simple circuit, the current will be maximum and resistance is minimum. So resistance is minimum means whatever the variable value is there, that value should be 0. Then this will be the maximum value here. So then in this case, the power delivered will also be maximum for the same condition here. So this small r is equal to 0, for that condition only will get this maximum power delivered here. So that maximum power delivered you can write as V square by R. So you need to remember this case here, especially this case. When small r is variable, the power will be maximum when internal resistance in the circuit is 0. Because our previous condition, if I apply here, we are getting like E square by 4R you are getting here, that power. But you can observe that now this value is greater than that of that previous value there. So that means you need to observe the difference between these two cases here. When capital R is variable, power will be maximum and small r is equal to capital R, and current will be maximum. Both the conditions will be different here. Current will be maximum when capital R is equal to 0. But in this case, when small r is variable and capital R is fixed here, then both current and power will become maximum for the same condition here when internal resistance of the cell is 0, right? And we discussed already these conditions at the grouping of the cells, mixed grouping of the cells. And now let us see a simple problem based on this, and that means in some circuits there is a simple way to calculate this, to apply this maximum power transfer theorem here. So that means, or we can treat it as some shortcut there. That means if circuit is given like this, we need to find this R value for which the power delivered to this resistance is maximum. So this is a given circuit here. Write this as a question. In the given circuit, find the R value for which power delivered to it is maximum. Find the external resistance R value for which power delivered to this is maximum, right? So then in that case, what's our general procedure to find that is, here that means actually these are not mentioned whether they are internal resistance or external resistance. Such information is not there. So only this resistance is a variable here, whether they may be internal resistance or external resistance, whatever it may be. So only this resistance is variable, and we need maximum power to be delivered to this resistance only, right? And so then in such a case, what our general procedure is, we cancel the circuit by removing this resistance here. Suppose I am taking the circuit like this by removing that resistance. The unknown resistance I am removing, and we are taking these terminals as some X and Y. And so now let us find the current in the circuit here. The finally our aim is to find the potential difference between this X and Y, right? And so to find, that means we are going to replace all these cells and resistors by their effective values. That is our main aim here. And so that I am finding the potential difference between these two values. For that we can find the simply current in the circuit here. You can simply calculate the current in that circuit there. So then that current in the circuit will be, you can write this as, like see this, these two cells, only current will flow here because we are removing that resistance. Then these two cells will be connected in oppositely here, then 18 volts you will get, and 18 by this 9, 2. Or you can apply the Kirchhoff law, then you will get this 2 amperes here, 2 amperes current. Then let us apply this potential difference we need to find here. The potential difference between X and Y we need to find. You may apply the Kirchhoff law along this in this loop here, so that you will get the potential difference between X and Y. And therefore this potential difference between X and Y you can write like this. 12 volts we are getting here. By applying the Kirchhoff law, you can calculate the potential difference. Just apply between this point and this point by following this path here. Like you can write this as Vx plus 10. And here current is flowing here. Current will flow in this direction here. So we are traveling opposite the current. So plus 12 plus 10 minus Vx. Sorry, Vy. I think this cell is connected. This cell should be connected wrongly here. So this cell, change the polarities of this cell here. Yeah, here polarities or they are giving correct only here, but symbols they are giving here. This is positive and this is the negative terminal. So change that. This is the positive terminal here. So here also change that. This is positive terminal and this is the negative terminal for this. So this plus is this side and negative is this side. So that here this value will get this value as positive minus sign here. Because now here we travel from positive terminal to negative terminal. Got it? And so therefore this value should be equal to 0. Therefore you will get this value as Vy. The potential difference between them is like Vx minus Vy or Vy minus Vx is equal to 12 volts you will get. So there is a potential difference between them. That means this total circuit we can, all these cells we can replace by this potential difference here. Potential difference between them is 12 volts we are getting here. Next, find similarly the resistance, effective resistance here. The effective resistance is nothing but this value, will get this value as 2 ohms here. These two are, and that means to find the effective resistance after this, to find the effective resistance, what's our procedure is, we need to short circuit these cells here. Instead of the cells, we need to assume a conducting wire here, right? So that means we need to replace these cells by a conducting wire, or we need to short circuit those cells. And then we need to find the effective resistance in the circuit here, except this R, that means after removing between this X and Y. So that effective resistance we are getting this as 2, because these two will be, once if you remove that resistor, then this if you are considering them as a conducting wire here, these two will be in parallel. So that means between this X and Y, we need to find the effective resistance by short circuiting all the cells present in that circuit. So then we are getting like this values as these two are in parallel, so we are getting 2 ohms here. So then we can redraw the circuit equivalently like this. So then we are potential difference between X and Y is 12 volts. So and Y is a higher potential what we are getting here. So positive plus 12 volts we are connecting, we are assuming to be connected here. And the internal resistance, effective resistance is 2 ohms. And then this is the circuit between this X and Y here. So then this is the resistance. Now we can easily conclude that now this circuit is similar to our discussion here. Previously what we discussed here. Now that circuit is similar to that. And so then in that case what we can write is the current or power in that circuit will be maximum and external resistance is equal to internal resistance. Therefore this R value should be equal to this 2 ohms here. So that is our resistance required here. So is it clear? When the circuit is such a complicated circuit is given and they are asking the condition for this maximum power. So this is the procedure you need to remember. We are removing this. If you are able to calculate the internal resistance directly, you can calculate that internal resistance and you can equate that. Or otherwise, this will be the procedure here. We remove that resistance, and between these two, we find the between those two across this resistance, we find the potential difference here. And after finding that potential difference, we need to find our next step is to find the resistance, effective resistance in that circuit. So effective resistance between these two terminals by short circuiting all the cells present in that circuit. So then after that you can convert this circuit into given circuit into such a simple circuit here. and from that you can apply this internal resistance must be equal to external resistance to get the maximum power in that external resistance there. So that is about this maximum power transfer theorem. And a lot of problems will be there based on this maximum power transfer theorem. So understand this procedure clearly there. And a lot of problems are there based on this maximum power transfer theorem even in our worksheets also, right? So then that is about the maximum power transfer theorem. And next to this, next topic is there like rated values and power consumed when two resistors are connected in series or connected in parallel, or like when bulbs are connected in series and bulbs are connected in parallel. I will explain that in our next class there, right? So then practice the problems based on this maximum power transfer theorem. Thank you.